Good evening. Welcome to the 33rd annual Emma K. Malmstrom Lecture in Physics here at Hamline University. My name is Andy Rundquist, and I serve as the interim provost of Hamline University. President Murray is under the weather, and she really wishes she could be here tonight, but I am here in her stead. I want to begin by taking a moment to acknowledge and honor one of our legendary alumni, Carl Malmstrom. After the passing of his wife, Emma K. Malmstrom, he endowed this lecture series as a tribute to her and the life they spent together. Carl was a constant fixture at this annual event all the way up until his death in 2010 at the age of 97. Carl Malmstrom was a physics and mathematics major in Hamline's class of 1936, receiving his master's degree in physics from Syracuse University in 1938. Carl's early scientific career was interrupted by World War II. He was a decorated naval aviator who served in the Pacific Theater and North Africa. Once he was out of the service, Carl put his physics degree fully to work and played important roles in the development of atomic energy. He helped form the Atomic Energy Department and worked on the H-bomb. He also spent time working with the Atomic Energy Commission. Carl was highly regarded within the physics community throughout his career and made a number of significant contributions to the field. Carl endowed this lecture as a way of not only honoring his wife, Emma K. Malmstrom, but as a way to give back to the Hamline community, providing us with the means to bring to campus some of the best scientific minds in the world. Over the years, we've welcomed many great scientists and given students, our faculty, and the public the opportunity to learn and to talk with and to learn from them. It was also abundantly clear that Carl enthusiastically enjoyed these lectures, always sitting in the front row center. He could hardly wait to ask a question or to lend some humor. We honor Carl for his generous gifts to Hamline and celebrate his legacy as we will continue to do so for many years to come. We are very proud of our science programs at Hamline. We attract and educate outstanding students who go on to do great things as exemplified by individuals like Carl Malmstrom. There are many things that distinguish our programs. One of the most important is the opportunity for students to work closely with faculty dedicated to helping them develop their interests and skills to the fullest extent possible. In fact, it is now my pleasure to introduce one such faculty member, Professor Lifeng Dong, who will introduce this year's Emma K. Malmstrom Lecture in Physics. I forgot about this page. Anyway, Professor Dong holds the Emma K. and Carl R.N. Malmstrom Endowed Chair in Physics at Hamline University. Professor Dong received his PhD and master's degree in physics from Portland State University after completing his MS in Materials Science and Engineering and BS in Mechanical Engineering at Qingdao University of Science and Technology in China. Professor Dong is the recipient of 22 patents and has published over 360 peer-reviewed articles and book chapters. An award-winning researcher, Professor Dong currently works with his collaborators and students on the design, synthesis, and characterization of nanoscale materials and devices for renewable energy conversion and storage, as well as water purification and desalinization. Professor Lifeng.
Good evening. When you come here, did you see any stars? Okay, it's great. For this 33rd EduK Malmstrom Lecture in Physics, it's my distinct honor to introduce our speaker tonight, Dr. Sara Seager. And Professor Seager is from the Massachusetts Institute of Technology, MIT. Her groundbreaking research ranged from the foundation of exoplanet atmospheres to innovative theories about life on other worlds, to development of novel space mission concepts. She was the Deputy Science Director of the MIT-led NASA's TESS mission and the principal investigator of ASTERIA Telescope, which orbits Earth from 2017 to 2019. She has also led efforts to design space mission to find another Earth. Right now, she leads a Morningstar mission to Venus, searching for signs of life in the cloud of Venus. Professor Seager has received many awards, including the MacArthur Genius Grant, and also exciting last month, she received prestigious Kavli Prize in Astrophysics. Congratulations. And one asteroid, 9729, is named after her. Please join me in welcoming Professor Seager.
Well, our story begins billions of years ago when a very simple life form, cyanobacteria, figured out something very clever. I'm not sure about you, but I don't view the bacteria in my fridge or the mold or anything as being clever. But this life figured out how to harness energy from the environment, namely photosynthesis. And in the process, ended up generating oxygen as a byproduct gas. That oxygen, over billions of years, saturated its sinks and ended up filling our atmosphere to 20% by volume. So you know, we need oxygen to breathe. And it is here in our atmosphere in large amounts. But did you know that without life, without plants, vegetation, and photosynthetic bacteria, we would have no oxygen in our atmosphere? It's so reactive, it has to be continually produced or there wouldn't be any. So if there's an intelligent alien civilization orbiting a planet around a nearby star, and they have the telescopes we're trying to build, and they look back at Earth, they actually will see oxygen here, and they'll be highly suspicious that there's life here. So what's really interesting is it's not from big structures like the Great Wall of China, it's not from pollution or city lights, but they're going to suspect there's life here because of a gas that doesn't belong. And astronomers figured this out like literally 100 years ago. And today we're the first generation who's trying to find signs of life beyond Earth by way of gases that don't belong in another planet atmosphere. So that's the kind of bigger picture. Not to do a spoiler alert, but we have a long way to go. So I can't tell you we're finding that right now. It's going to be a generations long search. So I'm glad there's a lot of younger people here because it's really your search. But I am going to tell you what we're doing right now. And just so we're all on the same page, our sun has planets, like Mercury, Venus, Earth, Mars, etc. Every star in the sky is a sun. And since our sun has planets, it makes sense that those other stars also have planets, and they do. And it appears that every star has planets. So the next time you go to the night sky, I guess it's not going to be tonight because it's cloudy out there, but you can look up at the stars and you can literally wonder what kind of planet is around that star. So I'm going to take you on this journey of what is out there. And to start with, actually what I'm going to do tonight is answer all of the questions I get asked most often. And these questions, you know, sometimes they're asked by my fellow scientists, they're asked by the people at the dog park, they're asked by kids. Literally at dinner tonight, I got asked almost all these questions. And some of you could probably answer some of these on your own, but one of them I get asked the most often. So when I get there, I'll tell you which one it is, but you can make your own guess yourself while you're looking at them. So the first one is, what is an exoplanet? Now I have an easy way to answer and a hard way, and I'm going to do both of those. So in the easy way, I'll walk you through a series of travel posters. We can't go to these other planets, but it's just to kind of try to capture what we think might be going on there. This one says Kepler 186f, where the grass is always redder on the other side. Because some planets, they're orbiting stars very different from our sun. Tiny red dwarf stars that are giving off a lot of red light. And so they're just imagining maybe there's red plants instead of green. Experience the gravity of HG 40307G, a super-Earth. There are planets that are more massive than Earth, but not too much bigger. So they actually have more gravity. So if you wanted to like play basketball on that planet, it might not go as well because the ball wouldn't be bouncing as high. But they're just imagining someone goes there and is parachuting and experiencing a kind of different world. Relax on Kepler 16b, where your shadow always has company. It's the land of two suns. There literally are planets that are orbiting two stars, circumbinary planets. We like to say sometimes science fiction got things right. Any Star Wars fans out there? Yeah. Okay, so that was the kind of simple way to introduce it. And now, just for this next part of my talk, I'm going to show you a series of graphs. So if you're not graphically oriented, then you'll just sit through this for a few minutes. And if you are, I will, oh, right, one more thing I forgot to say, that one of the big things in this field is planets that go in front of their star as seen from our viewpoint. Now, all the stars have random inclinations for their equatorial plane, but I want you to think of like a planet that's orbiting edge-on, so it's going in front of the star as seen from our viewpoint. Now, it could be orbiting a star in the plane of the sky. We would never see it go in front of the star. But there happen to be ones that do, and we call them transits. So let's watch that one more time, because we don't spatially resolve any stars like that other than our sun. Instead, we see the graph at the bottom. Do you see the difference? Planets going in front of the star. We literally measure the brightness of the star as a function of time. And if there's a planet going in front of the star, we get a tiny drop in brightness. And that drop is related to the, it says right here, the planet area to the star area. So you remember pi r squared planet over pi r squared star. So if we know the r of the star, if you know the size of the star, you can actually measure the size of the planet by that drop in brightness. And it looks like a squiggly line because there's noise in the star, there's noise in the telescope. And I just learned that the new telescope that the physics department got, like I'm not going to try to over-advertise for you folks, but apparently you can do a project and you can measure a transiting light curve of a star, of a planet going in front of it. There are so many of them that every clear night, don't quote me on this, but I believe that every clear night there is a transiting planet that's like about a 1% drop in brightness that we can observe if we know where to look. So we have these transiting planets. We can measure the size of the planet. We have another method where we can measure the mass. So what is mass over size cubed? Mass over volume? Density. That's why in exoplanets we've sometimes been, okay, sometimes people said exoplanets. It's interesting, but is it physics? Because some people think it's too simple. We have mass, we have volume, we get density. Okay, so we have density, and I'm going to walk you through these plots, and you can just enjoy the aesthetics of them, but some of you, you'll get what I'm talking about. This plot, it is showing you planet mass in Earth masses and planet radius in Earth radii. This is on a logarithmic scale, so look how big it's spanning, 1, 10, 100, 1,000. And this is radius, 1, 10. So we have Earth and Venus here, 1 Earth size. We have Uranus and Neptune, Saturn, Jupiter. Now what these curves are, I'm going to explain them briefly to you. They're like illustration curves of something of constant composition. So just for illustration, if we could have, which we don't, like a planet of pure iron, that would be the bottom curve. The yellow curve is like rock. This curve is more like water. But there's something interesting about these curves I want you to all appreciate. Let's imagine it's like a great winter day and you're building a snowman. You take your snow, and as you add more mass to that snowball, it gets bigger, right? In fact, it gets bigger as r cubed. So you keep adding mass, it gets bigger. But what this graph is telling you is that if you keep adding mass to a planet, a fictitious planet, 1 Earth mass, 10, 100, 1,000, like it literally stops getting bigger. Isn't that weird? Like these curves flatten out, and I'm going to come back to that. How could you be adding mass to your fictitious planet or like your snowball, and eventually it is so massive it stops growing? Like, how does that make any sense? You can think about that while I walk you through these graphs, and I'll come to that answer in a moment. So this is showing you times. This is 1999. We only had one planet, this little pink one, where we had a measure of a mass and size. There was only one planet that went in front of its star as seen from Earth that we knew about. And I was just going to kind of show you this little travelogue over time. 2001, not much happened early on, but look what started happening. We started finding more and more of these planets that go in front of the star, for which we had both a mass and a size. Now what you notice by 2008 all the planets are like in the top right of the diagram, because initially we can only find really big planets. Big planets, they're easy to find, they have a big signal, they cause a big drop in brightness. But over time, look how this diagram started getting populated. So if you don't understand the graph, you don't have to understand the graph to understand the rest of the talk, but you can at least appreciate that how many of these we're getting. And we're going down here to smaller and smaller masses, even some Earth mass planets. Now, it's just astonishing. We have way more than are on this graph. This is just a subset, but look at that, huh? Just amazing. I started working on exoplanets in the mid-1990s. We had maybe 1 or 2 planets. There were no transits. People thought this field would dead end. They thought the field would go nowhere, and many people told me not to bother. In fact, even these transiting planets, there was one, people just thought it would go nowhere. But nature was kind to us. What you see on this, see how like their planets are everywhere. They come in almost every mass and size and orbit, and it's absolutely astonishing. You know, this would be like for humans, we have a kind of average height. Maybe some really short people or some really tall people, but on the whole, there's just a very narrow range. The planets aren't doing that. They're literally coming in every mass and size and orbit. So I like to say that in exoplanets, anything is possible within the laws of physics and chemistry. So let's come back to the thing that each one of these is a different planet. So we have some planets, this is Jupiter here, this is Jupiter. We have some planets, they are about the same mass as Jupiter, because this is mass, so any planets along this line I'm drawing, wait, let me think, sorry. I meant to say this. We have some planets that are the same size as Jupiter. So this is Jupiter's size here, about 11 or 3 radii, but they span a factor of 10 or more in mass. That's what I was trying to put to you a little puzzle at the beginning. How can you have a planet that is the same size, even if it's 10 or 100 times more massive? That makes no sense at all. I don't know if anyone figured this out. But what is happening is the planets are so massive, they are compressing the interior. And they're compressing that interior so much that it's what we can call pressure ionized. Electrons are popping off because the inside is so high pressure. And once these electrons pop off, the nuclei can squeeze closer together because we don't have as much Coulomb repulsion going on. So it's like if there's one physics fact you can take away, it could be that you can just keep adding mass and the object stays the same size in some cases because the inside is compressing so much. So in this diagram, I mean, there's a lot we could do for it, but mostly I just wanted you to see just how many planets there are and how many different sizes and masses and orbits. And you know, you can try to pick this apart, like there seems to be missing planets here. There actually are. There's a lack of planets of this size. We have no massive planets. We have no really big light planets. But that maybe is for another day. But here at least, I aim to answer the first question. What is an exoplanet? It's a planet that orbits a star other than the sun. Thousands of exoplanets are known. We expect that every star has a planetary system, nearly every star. And I tried to capture with the posters and the graph just how diverse the planets are. There's so many different kinds of planets out there. All right, so the next question I get asked is when and how will we find another Earth? Well, the problem isn't so much that an Earth far away is faint. It's not fainter than the faintest galaxies we would ever have observed with the Hubble Space Telescope. The problem is that an Earth would be right next to a sun. If we want to find an Earth twin, another planet like ours, it would also be right next to a sun. And so the problem is not so much it's so faint, the problem is really that it's next to this big, bright, massive star. And that makes it very, very hard. In fact, any planets we find, it's really dwarfed by that star in so many ways. Well, we have lots of ways to find planets, and I've just listed 3 here. We can do one that relates to the planet size. There's another technique that relates to planet mass, and there's one that relates to planet brightness. But I was trying to give you some numbers to show you how hard it is. And when I explain these numbers, I want you to think about what method would you choose. If you were going to drop everything for a while and look for planets, would you choose a method that relies on planet size? Our Earth is 100 times smaller than our sun, or 10,000 times in area. That would be like if you're going to build a deck on the back of your house, and you're going to buy some planks, wooden planks, or the fake wood. Would you be measuring that to, let's say, 15 feet, or would it be 15.01 foot? Or would you go 15.0001? Like, you'd never go to that many decimal places. So I'm asking you, would you pick a method where you have to go to 4 decimal places for area? No one likes that one. Well, do you want to go to one that's on mass? Now it's 300,000 times less massive. So when you're making your measurement in the combined planet-star system, you now have to go to 5 decimal places. Well, if you want to do it in reflected light, so now imagine you want to look at it in brightness difference, our Earth is 10 billion times fainter than our sun. And I dare anyone to tell me if you've ever measured anything to 10 decimal places. You know, sometimes I ask that and people have, like not just for your everyday life, but they work on some obscure physics thing and they have to go to that many. It's crazy. Well, which one? Well, I don't know which one would you do. Like, should we really be taking the easy way out and go for the easiest method? Yeah. Okay, yeah, that's what we're doing. Yeah. It's not always the case, but in this case we are. We're going for the easiest method, and that's what we started out by talking about. This is today our most popular method of finding planets. We're looking for the drop in brightness. And remember I told you it's the area ratio. The planet area, pi r squared of that dark blob around compared to the area of the whole star. And that's that drop in brightness. And you know how we do that? One way we do it is we have this is an artist's conception of an MIT-led NASA mission called TESS. TESS is 4 glorified telephoto lenses bolted to a platform. And this is just showing you the area that they cover in the sky. This orbits Earth in a very, very long elliptical orbit. Each camera has what is a pretty big field of view, actually. And all the cameras together, they're made so they monitor a giant strip of the sky for 1 month. These transits are rare. So you have to look at like tens of thousands of stars at one time. If we tally up all the stars, it's literally millions. And TESS, and then it stares at this one section of the sky for a month, and then it tiles the entire sky in 1 year, each hemisphere in 1 year. And it's launched in 2018, so it's still going. It's in a kind of really weird orbit in resonance with the moon, and it's such a stable orbit, it literally doesn't have to do barely any orbit correction, and honestly, supposedly it can last for like 1,000 years in that orbit. So TESS monitors all the stars at once, and a computer looks at those millions of stars, trying to find that tiny drop in brightness that is characteristic of a planet. And each camera is so big, the constellation Orion would fit in it. So it's really hammering away at all of these. And I'm just giving you a mini snapshot. I know it's a lot of information for just a snapshot, but here's just a tiny portion of the sky. And for those interested in, I know there's some classes in data crunching, but essentially millions of stars are monitored at once. These sophisticated computer algorithms measure the brightness of each star for every frame. And then they search for this. They actually do most of the work, but you know what? I don't know if you all will trust the computers to do everything, but at the end of the day, it goes from like tens of thousands of stars every month to a few hundred. And we literally have humans, our brain is still the best computer, honestly. You know what it is? Because you all have AI, right? Like you use ChatGPT or you do AI somehow. Why it's so hard to, we do use AI as well, but it's so hard for us humans, actually, to create fake noise. Like the noise in the data, just from the instrument and the stars themselves, it's nearly impossible for us to simulate that. But anyway, so we eventually have humans who go through all the 300 or so that the computers told us are likely planets, and we then kind of upvote them in a way, and then they go out to the community to check with lots of ground-based telescopes to find out if they're really planets or if there's some kind of false positive. But that honestly is a whole talk in and of itself. I just wanted to give you a snapshot of how we find planets. But the problem is that for our Earth and Sun, our Earth is so tiny. See it on there, that little fake dot compared to the Sun? This area ratio is, where we talked about it, it's 4 decimal places. And we talked about how that's a tiny number. No one here builds your deck or measures things to 4 decimal places. So we're doing something even easier. We're not only using the easiest method, we're taking it a step further in favorability. I do feel like it's kind of cheating, But what we're doing is we're going after small stars, much smaller stars than our sun. There are these small red dwarf stars. And if you look on the far right, that's a cartoon of I forgot to mention, the one on the left, our sun, it's a real image of our sun. And the dot there is fake. But see the far right, it's the same size fake planet. But see how much area it takes out? That area ratio on the far right is 1%. So going to 0.01, I think everyone's going to agree that's a lot easier than 0.0001. And that is a tiny star. It's actually modeled after a real star. Has anyone heard of it? Called TRAPPIST-1. It is actually so small that any smaller and colder, it would not be a star. It would not be able to fuse hydrogen in its core. So yeah, we're going after these really, really small stars. So just to give you a handle on what that's like, I wanted to take a little mental break. Oh, right. I was just So I don't think I'm allowed to assign homework, but if I was, I have this little snapshot actually, because what I'm going to talk about later in the talk is talking about exoplanet atmospheres. Okay, we're going to talk about that a little later. But what it is there, see the fake atmosphere in light blue? I think everyone here remembers how to calculate the area of an annulus, right? Don't look so panicked back there. But the area of the annulus compared to the area of the whole star, it gets harder now. And I was going to explain to you, I'm not going to do it though, but how to calculate that area, because we can estimate the area by, I'll just say it because I know there are some physicists in the room, but basically you take hydrostatic equilibrium, what holds up the atmosphere, the pressure gradient force against gravity, and you use the ideal gas law, assume the whole atmosphere is the same temperature, and then you actually can derive the height of the atmosphere. It's called the scale height. It's like when the people hike up Mount Everest, they run out of air because the atmosphere is thinning rapidly. And we can actually work out how rapidly that air is thinning out, and that's how we can estimate the size of the atmosphere, yeah. So it would take you an hour to explain that to you, so let's not do that. We'll take the mental break, and we'll go on a virtual trip to a planet orbiting an M-dwarf star. So let's imagine for a moment we could go there. This is an artist's conception, and the artist has made the star very big in the sky, the sun, because these small stars, they give out very little energy. And so for the planet to be the right temperature for life, to be warm enough, the planet actually has to be very close to the star. So in some configurations, the star might be very big. Usually it doesn't look that big, but big. And this artist also made they made the sky a different color just to keep your interest. But what's really interesting, when a planet is so close to the star, due to tides, over just like tens of millions of years, the planet ends up being in a very favorable energy state. It takes one time to rotate for every time it orbits. It's what we call tidally locked. Just like the moon, have you noticed? It shows the same face to Earth at all times. You know what that means? People don't usually think about it. The moon is rotating one time for every time it orbits because it always shows the same face to Earth. That's because tides over time, they want to line it up. It's a favorable energy state. But for this planet, if we could visit it orbiting the star, if the planet is showing the same face to the star at all times, that means one side of the planet is always in day, and the other side's always in night. So which part of the planet would you want to visit? Would you want to go where it's always day? Well, the right answer is where it's always night, because it's an astronomy lecture. Yeah, always night. Well, actually, honestly, I would want to go where the sun is always setting. But they wouldn't call it sunset because, it wouldn't be changing. I just love to imagine intelligent beings on one of these planets, and they'd be talking about our planet Earth, and they would be saying, like, it has a day and night, that's just so crazy. How could anyone, handle that? How would you go on vacation? Because, where would you go? And they have seasons. They have no seasons on this planet. It's kind of weird, actually, yeah, because it just simply means that that star, the sun, is in the same place in the sky at all times. Now, being very close to the star, it also means, due to Kepler's third law, the planet orbits the star very quickly. So these planets that are the right temperature from the star for life, they would be orbiting their star in about 10 days. So every year would be 10 days. So I don't know if there are any kids in the audience, but your birthday would literally be every 10 days. Yeah. I think they probably operate on century timescales, right? So every 100 days, maybe you get your birthday then, yeah. But, you know, on second thought, us visiting this planet, even virtually thinking about it, would actually be a terrible idea. Because these small stars, they're very magnetically active. They give off flares, and you couldn't be glued to your phone because those high energy particles would destroy the electronics. I think these flares are really bad, actually, and I do imagine, I love to imagine life there. It would be like, here in Minnesota, I hope you still get snow days where you get a lot of snow and they shut school down. Yeah. Yeah, they tried to take those away in Massachusetts, you know, after COVID because of online school, and there was like a rebellion, so now they still have snow days. But I imagine on this planet, if there is life on a planet like this, I imagine they have radiation days. They see the flare coming, and it's so big, it's not just going to give them some nice northern lights, but the flare is going to make it so dangerous that you'd have to like go, you know, in your underground basement and just stay there for a couple days till it dissipates. In fact, here on Earth, about 150 years ago, we had a really bad flare event called the Carrington event. Has anyone heard of that? Yeah, a lot of people have heard of it. It's kind of scary, actually. Our sun gave off a giant, it had a flare, it gave off a giant piece of our sun, actually, a small piece, came hurtling towards Earth. And right before that, an amateur astronomer named Carrington, he was studying sunspots. And he saw the sunspot brighten, and he wasn't sure it was happening. But a day and a half after he saw that, our Earth literally became electrified. You could see the northern lights all the way down to the equator nearly. And they lasted a few nights. And they said that here in Minnesota, you would have been able to go out at night and literally read a book by the northern lights, they were so bright. Now, we didn't have an electricity grid, but we had telegraph wires, which some of them caught fire. And what had happened was this part of the sun came hurtling towards Earth, and it had a magnetic field embedded in it, which hit our magnetic field and induced a current, and that's what happened. And I used to say like no one died, it wasn't that bad, but one or two people, yeah, they definitely died. But these TRAPPIST-1, this small star, it was caught in a field of view of the Kepler Space Telescope, and people counted 40 flares in 80 days. And they estimated that one of those flares was equivalent to the Carrington event. So instead of every 150 years or so, the stars, some of these small red dwarf stars, they're giving off like lots of energy constantly. So it's not a great place necessarily. Here's a satellite image of our sun giving off a coronal mass ejection. And it's looking all mottled because it's a very narrow wavelength where it's observed at. So how will we find another Earth? Well, we're not going to find another Earth right now. Instead of finding the Earth twin, I call it the Earth cousins. We're taking the easy way out. We're fast tracking to find what is easier to find. It's not necessarily like Earth, and we're also going to use the most favorable planet finding technique. So we're doing the easy stuff. So if anyone here wants to work on exoplanets later, it's going to be harder because we're doing the easiest thing we can. So we get to the next question, can we go there? Now this question is the one I get asked the most often. Yeah. And on my way here yesterday, I've been binge watching The Three-Body Problem. It's such a great movie, yeah. The book is really much harder to read, but it's a crazy story. So I encourage you to read it, read the book or watch the Netflix simplification. Can we go there? Well, the thing is that the stars are just so far apart from each other. It's really hard. We can't do that now, but here's a picture of our sun. And let me ask you this, is how big do you think our Earth is compared to the sun? There's a hint on here. It's a star spot, that's a sunspot that is the size of our Earth. We're just trying to do some scaling exercise here. Now, if that is our Earth compared to our sun, how far away do you think Earth is at that scale? You can raise your hand if you think it's where it is. In astronomy, we always like to simplify things to round numbers. So it turns out our Earth is about 100 sun diameters away from the sun. So where would that be? It's not in this room, but maybe it's out in the street. It's far, right? I mean, the distances are huge. Well, if this is our sun, where do you think the nearest star would be? Wisconsin, okay, not a bad guess. Another guess? Yeah, that's the size of our sun to scale, and I gave you the Earth. And our Earth would be 100 suns away, but where's the next star, the next sun? It's so far. It's like LA, basically. It's unbelievably far. Yeah. Pardon me? Oh, good. Okay, great. So tell me where if it was a bowling ball, where would it be? Oh, Barcelona. Okay, great. Okay. So I think LA might be right here. I actually didn't do the calculation. I'm just guesstimating right now. Yeah. So bowling ball's like this big, and that star's like this big. So if it was like half the size, it would be half the distance to Barcelona. So it wouldn't be LA, but maybe it would be halfway from here. Yeah, it would be past LA. Great, I'm really glad you did that. It's so far. Like, think of how far that is. So we can't go there right now because our fastest spacecraft would take nearly 70,000 years to reach the nearest star system if it was traveling in the right direction. So that's not good. Yeah, not for now. Can we go there? Not for now. But here's the thing, is that in exoplanets and the search for signs of life beyond Earth, you know, the line between mainstream and crazy is constantly shifting. Because when I started working on exoplanets, it was so crazy. Like, people thought it was going to dead end, there would be no jobs, it would just not happen. Not go beyond the first few planets, because remember, the star is so overwhelming. People thought that our technology would never get better. But one cool thing is, you know, someone has to move that line. Like, someone has to do the thing on the other side of the line where it is so crazy to change our minds about what is possible. So I'm not saying it's possible to go to the nearest star, but I am going to give you a fact of a plan underway to develop technology to send thousands of tiny spacecraft zooming by the nearest planetary system. These are called, instead of spaceship, it's called space chip. It's actually called Starshot. And the program's a bit on hold now, but it was given $100 million to get it not to work, but just to burn down some of the tall technology poles. These would be tiny chips, just like when the little turtles are born. They're not all expected to survive. So you'd send thousands of them, and they would launch, they would deploy a solar sail on the order of 2 meters diameter. I know it's gonna sound a bit crazy, but there has to be like a square kilometer of telescopes with lasers correlated with each other that would then accelerate these sails without vaporizing them to about a 20th the speed of light. So there's a lot of tall poles there that have to be solved. But putting $100 million on this project and farming that out to different universities across the nation to try to solve some of these problems, they're not expecting it to work, but it's to change our minds that maybe it is possible one day. And that wouldn't be us going, but it would be sending these space chips, accelerating them to 20th the speed of light. They would still take 20 years to get to the nearest star system. They wouldn't have a way of slowing down, but they could snap some photos to send back to Earth. So that's kind of really interesting, actually. And so that is ongoing, and hopefully that will go somewhere. But you know what I always love to ask an audience is, let's say we figured out a way to go there, and to go a 10th the speed of light, and our nearest star system is 4 light years away. So it would take 40 years to get there. Now let's say we had a way to do that, and you could go on this spaceship and, you know, live there and travel. Who would go? Would you go to the nearest star system? There's always people who will go, like for sure, because we want to explore, like we want to do this. And you know, the best age, if you're like around 20 years old, you can take those 40 years, then you'll be around 60, and you know, 60 is the new 40, right? So you'll still be like healthy, right? So it's a great age for it. And what if I told you, because you weren't thinking clearly necessarily, it's a one-way trip, right? Because we don't have anybody to get you back. You would still go. I mean, there are always people who will do this, and I think it speaks to the human spirit that we want to explore. So now we get to the last question. These are literally the questions I get asked most often. If we can't go there, why look? Like, people are literally, we're finding planets, we want to go there, but they're so far, why are we doing it? And that's going to take a bit of time to unpack, but you still look like you're a bit energetic. You know, remember before I told you that science fiction gets some things right? Well, science fiction got some things wrong, because in Star Trek, any Star Trek fans out there? Yeah, Star Trek, it took, the Enterprise had to travel at enormous speeds to get to the nearest planet so that Spot could use his planet analyzer and see what was there. But it turns out, you know, if you wanted to make a movie of how we're looking for life elsewhere, it would be so boring. It would be like watching paint dry. Because we are using the Hubble Space Telescope, we are using our new telescope called the James Webb Space Telescope to study exoplanet atmospheres. And we're doing remote sensing, so we're not going to go there, but we can use our tools to study them here. And I'm going to just tell you about that. This is for the last part of my talk. It's going to take a little bit of unpacking here, but you've all seen a rainbow. And if you could look at the rainbow really closely, you would see that some of the colors are missing because of gases that are absorbing, gases in our sun's atmosphere, gases in Earth's atmosphere. They're taking away light because atoms and molecules all interact with light. But just so you know, like Earth and Venus are about the same size and mass, but we would need to look at their atmospheres to really know how they're different from each other. And remember when I started the talk and I said that on our own Earth we have a lot of oxygen, and that's a sign of life from far away. We need to study atmospheres in order to search for these signs of life. So I'm going to now share with you how we're studying atmospheres, and it goes back to the transit, which you're now all familiar with. Okay, so we have here a real transit taken with the James Webb Space Telescope, and there's relative brightness, so the star is just a constant at 100%, and over time, when the planet goes in front of the star, remember, we don't see the picture on the top. That is just an artist's conception. This is all we see, the point of light in a time series. And if the planet goes in front of the star, we see a very characteristic drop in brightness. Okay, so is everyone with me on this? Well now, if you look at this dark part of the planet, remember, pi r squared planet over pi r squared star, this has a fake, very, very exaggerated atmosphere. When there's an atmosphere present, what happens? The planet looks bigger. And now what will happen to that transit light curve? It'll be bigger. But here's the thing, remember the rainbow picture? Only some wavelengths absorb, others do not. So to study and find the planet atmosphere, we're literally looking for the planet changing size as a function of wavelength. Imagine we're observing with our telescope at a wavelength or color where the atmosphere is transparent, so there's no absorption happening. Then the planet is the size of this black disk. Now let's imagine we're observing at a different wavelength where the atmosphere is very strongly absorbing. Now the planet looks a tiny bit bigger. So we're looking for a change in planet size as a function of wavelength. I just want to make sure everyone gets that because I want you to walk away with understanding how we study atmospheres. So remember, the drop in brightness corresponds to the planet area over the star area. There's some wavelengths where the atmosphere is transparent. There's other wavelengths where it's fully blocked. And we get a change in size depending on what wavelength we're looking at. Okay, ready to try it? We have some real data here from the James Webb Space Telescope. And we have the relative brightness. Now it's normalized to 1. And it's a function of time. This is a few hours. The black is the best fit. It's like the average, basically. And these points are different wavelengths, or different colors, if you will. So your job is to see at what wavelengths, is any, is this transit, are the points, the data points, deeper than the average. I'm asking you, where is the planet looking a tiny bit bigger? Did everyone see that? I'm going to let it keep running for a moment. So we're looking for a wavelength where the planet looks a tiny bit bigger because of the effect of the atmosphere. Now, if you're coordinated enough, you can look at the drop in brightness and look at this as wavelength, W, in microns. This is the infrared. So now I want you to try to see if you can coordinate what wavelength it's at. You can just shout it out if you see it. Wow, I mean, let's let that land. You have seen evidence of an exoplanet atmosphere by eye. I mean, that is amazing. And that is due to our amazing space telescope and literally 2 or 3 decades of hard work by astronomers and engineers. Okay, so now, to make sense of all this, and if this was a class, you could do this in a class, you could literally measure this drop in brightness. See how it's 0.98, so that's 2%. We literally could, fit this data and measure this for every wavelength. And that's how we end up plotting the data out. We're now asking ourselves how much light is blocked as a function of wavelength. It's about 2% or so, or this says like 2.1%, except at these wavelengths, more light is blocked, up to 2.25%. And that's what you were all saying is 4.3, 4.4. If there was no visible atmosphere, these white points are the real data. The blue is a model. This is wavelength of light in microns, and this is amount of light blocked. So if there's no sign of an atmosphere, all these white points would make a straight line. So I think you can all agree with me it's different from a straight line. And that's an exoplanet atmosphere. Now this gas that is so strongly absorbing, it's actually carbon dioxide. And you've all heard about what a potent greenhouse gas it is. It's really like skunk spray. You just need a tiny amount to make a giant signal. So that's carbon dioxide, and this is a giant planet. It's a big giant planet atmosphere. And if we looked at it at other wavelengths, we'd see a whole bunch of places where there are molecules. There's carbon dioxide, there's water, there's some sodium. This is like a whole field of research now, and I'm really proud to tell you that this whole method of finding atmospheres, I invented that method 25 years ago. So I'm coming towards the end of my talk now, and I hate to leave you hanging, but I'm gonna have to, not because I'm running out of time, but where the field is at now is we can get these atmospheric features for big, puffy, giant planets. These planets are blocking out a lot of the light. They have giant atmospheres. What we'd really need to do is go down to small rocky worlds with very thin, tiny atmospheres, and we're not really there yet. And it's kind of a weird thing in research because I'm gonna tell you, in class you'd be learning about physics or math, and then the professor would be like, here's your homework, you can solve this problem. There's a known answer. What I'm telling you now is in research, we don't have a known answer yet. We're struggling to get down to the tiny, tiny numbers for atmospheres of small planets with small atmospheres. But we think we can do it, but we still have a bigger problem. Atmospheres are complex. Remember, these stars and planets, we're not spatially resolving them. All we're doing is observing the light passing through the atmosphere. It's all averaged out. Imagine our Earth here. We're here in Minnesota. You could go to Florida or Hawaii. It's very different. But from far away, no one can see those differences. All the atmosphere, everything's just all averaged together. We have no details. And so it's a bit of a struggle right now. We have to ask ourselves, what molecules does life produce? Can a dead planet fool us? A planet with volcanoes giving off gases? How do we interpret limited data? And how do we quantify our uncertainties? This is pretty crazy because for every gas, we have so many gases made by life, thousands of gases. But for each of these gases, I could literally come up with a gas that could be made by life elsewhere, and you can come up with a counter-argument and say, no, I have a way that chemistry could make it, or geology. And so right now, I do have to leave you hanging because we're kind of stuck. We're trying to sort through all of this, and we're not there yet. I'm gonna skip some of this. So if we can't go there, why look? Because we're doing remote sensing with space telescopes. And this is gonna be a generations-long search. We have many new telescopes coming online. We have the new paradigm of starshot and other ways. But ultimately, it's going to take us a lot of effort to sort through all the options and to think about what new telescopes we're gonna need to finally get the job done. All right, I'm gonna summarize the answer to all the questions now. What is an exoplanet? It's a planet orbiting a star other than the sun. When will we find another Earth? We're not able to do that. We're doing a fast track. The easy way out, we're looking for the Earth cousins around the small red dwarf stars. Can we go there? I gave you a mixed message. No, we cannot. But someday we want to, although it's probably not us. It's going to be sending probes there. If we can't go there, why look? We're doing remote sensing. And I just want to say that even though I left you hanging and I told you it's for the next generations to really solve these problems, it's been incredibly exciting to be part of the first generation. And I hope I've been able to convey some of that enthusiasm to you of what it's like to look for planets and unravel the mysteries beyond. Thank you very much.
That is great. So any questions?
Your definition of an exoplanet, would a rogue planet be considered one?
Good question. You know, we think that every solar system or every planetary system has expelled its excess planets. You know, it's crazy, but every system seems to be what we call dynamically full, that they formed with more planets and kicks them out. And there are probably just planets, rogue planets floating around our galaxy. Are those exoplanets? I mean, yes, I would call it that. And it's a bit unfortunate because we're not English majors. We have done a poor job in a lot of the words we use in our definitions. So maybe someday we'll have a more encompassing definition of one. And that day will probably happen about 5 years from now when a new telescope goes up. It's going to be able to find rogue planets. And then we'll have to get a better definition of exoplanet.
Thank you. Other questions?
So what are some of the things that could dim a star that would maybe make you think there's an exoplanet but it really isn't?
Great question. What are other things that can dim a star to make it look like an exoplanet, but maybe isn't? Like if you were paying attention and it went by a bit fast, there's a really characteristic shape. And that shape is really, really critical. But you know what the most common other thing is? It's related to two stars. There are a lot of eclipsing binary stars. They go around each other. But an eclipsing binary star makes a giant drop. But what is this? It's eclipsing binaries with a giant drop in brightness. But there's a third contaminating star that just happened to land on the same pixel, or maybe it's a third star in the system that washes it out to make it look like a shallow event. So in fact, the binary stars, there's so many of them out there, and they are the biggest contaminant. Other times, the transits aren't as nice as I showed you. They're very noisy, and you can't tell if it's like just noise or if it's a real signal.
So in that initial graph you showed us, why isn't there more like rocky planets, large rocky planets?
The more massive rocky planets? Good question. Why are there not more massive large planets, like 100 Earth mass planet? Because we think what is happening, and this is what people have thought for a long time, is that when a planet starts forming, it becomes massive enough to act like a, I know you're going to laugh at this, but it acts like a kind of like a planet vacuum cleaner. And then it's so massive, it can gravitationally attract all the gas and all the material around it. And then it goes into a runaway phase and becomes big. So the thought is that you never stay a rock. If you become a big enough rocky core, then the planet's able to accrete material and grows rapidly. So that's what we think happens. What's my favorite science fiction book? It's a good question. I mean, I love all the books. I love all the science fiction, actually. Right now, I'm pretty into the three-body problem because I have to read the book. I got it as a gift. And I don't know about all of you folks here, but the people who are students, like, you don't read much, I'm sure. Because I have kids your age in college. And it turned out they used to love reading, you know, and Harry Potter and everything. And there came a time when people just don't really read anymore. So my one son, one day he messages me, what's the three-body problem in physics? And I'm like, why do you know? He's like, well, I bought you this book for your birthday, but I'm reading it. So I realized it must be a really good book, right? If someone who's not used to reading, like, will actually read. And then I started reading the book, and it's just an incredible story, but it's a very complicated story, and it involves a lot of different things. So I think that one right now is my favorite, because it's pretty, I don't want to do any spoilers here, but you can also watch the Netflix sort of simplified version, which I really needed help understanding the whole book, so I appreciated the simpler version, but I'd say it's a three-body problem.
Earlier on, you showed us the graph of the masses and the radio of the planets, and you said that when as planets reach certain mass, the nuclei in the core starts to emit some electrons and stuff. Is there a name for the limit where that becomes the exoplanet's mass?
Is there a name for where it turns over? Like, oddly enough, there isn't one, actually. Like, there could be, yeah. But no, there's no name for that.
Oh, that is way back there.
Yeah, I had a question about, you said that you can detect the different wavelengths, and then those let you know what type of gas it is. but that you could be fooled because it might be a volcano or something. Is oxygen ever tricky like that, or is it always faithfully a sign of life?
Yes, oxygen. Does it have a false positive? Could it be made without life? You know, for the longest time, oxygen was like our most robust case. But as we're getting closer to the time we hope we might detect it, it's like a little cottage industry of ideas popping up of how you could make it without life. And if you get, I don't know what you folks get in your newsfeed, but one time I got this really interesting story about some like minerals, but I've forgotten the chemistry, at the bottom of the sea that are putting out some oxygen without life, actually. And people have a lot of ideas, like they say, for example, on some planets, without the cold trap, like you know how we have water vapor and it goes up and makes a cloud, but it doesn't just, the water vapor doesn't keep going up. It gets so cold it turns into a solid. Well, if you didn't have our so-called cold trap and the water vapor could keep going up, it would go so high in the atmosphere that sunlight would break water apart and the hydrogen would escape to space. And then oxygen could build up for a while. So there are a lot of theories and people go back and forth. So right now, there's probably, out of a bunch of ideas, there's still probably a few legit ideas about how oxygen could be made. Yeah, how it could be made without life, unfortunately. People are more big on the combination of gases. So if you saw oxygen and another gas, like methane, two gases that shouldn't coexist, it would give you a stronger certainty.
The strongest telescope can see one.
Can the strongest telescope see?
See one planet.
Like see the planet?
See Mars.
See another planet like that?
Yeah, it's impossible. Yeah.
Right now, well, yeah, so like I said before, there's so many ways to find planets. One method, I'm just going to explain it, it's called direct imaging. We block out the starlight so we can see the planet directly. Now, you wouldn't see it like Mars. You would see just a point of light, like the pale blue dot. You couldn't spatially resolve the planet, but one day we want to see planets shining on their own light. Today we can do that, but it's for a really strange type of planets, big, massive planets that are young, that are shining from their own energy, not energy that's left over from their formation. So we can see that, but they're not normal planets.
Also, all these observations are done within the Milky Way, right?
Yes,
Not outside.
that's right. All of the observations are done within our own galaxy. There are hundreds of billions of galaxies. We can't reach the other galaxies. In fact, if you think of it, it would be like your local neighborhood, meeting the people in your neighborhood, not in like Wisconsin or Europe. We can only search our local solar neighborhood even. It's not even the extent of our whole galaxy.
Piggybacking on your explanation about oxygen not being found in like the atmospheric composition, how does water vapor play into this? Is it being found in the compositions of these atmospheres? And off the earlier question, could a dead planet be giving off signs of water vapor, or is that like a clear-cut signal of potential life?
Yes, well, water vapor is a sign of liquid water oceans just for small rocky planets. Like it normally exists in giant planets, but in small planets, the water should be photodissociated and the hydrogen would escape to space. But the ocean, if it's there, it can continually replenish water vapor. So we like the idea of water vapor as a sign of habitability, let's say. But we actually ran into another problem. I didn't have time to, dump all my problems on you. But one of the problems is these small stars. I told you how they're magnetically active. They have a lot of flares. They have a lot of spots. Well, those spots, they also have water molecules in small stars. And we're getting contamination right now. So we're struggling to find signs of water vapor, because if your background star isn't like perfect and homogeneous, it's creating some trouble. So we're trying to find water vapor in the small rocky planets. It's kind of next on the list. But if any of you have been lucky enough to go to Hawaii, or somewhere where there are volcanoes and there's vents, there's like steam coming out of the ground and there's sulfur gases. So yeah, a dead planet can be giving water, even without an ocean. It can be giving off some water vapor from the ground.
I have a question.
Sure.
Why did you assume that all suns have exoplanets?
Why did I assume that all suns have exoplanets? We have evidence that nearly every star has planets, and it comes from all the observations over all the techniques. I just said nearly all because we're not 100% sure, but from all the different methods used, There are just so many, there's statistics being done and methods being done. They're not like 100% robust, but quite confident that they all do. And I just left a little exception because we also see planet-forming disks. We see stars being born, and they all have leftover disks of material that we expect to form planets. Yeah.
So when in the life of a star are the planets created? Is it early in the life? Or
It's early. It's very early. And we have telescopes. It's a whole, like this field is so big, I couldn't possibly convey it all to you, but there are telescopes that study stars where the disks are there, and they see like dust lanes. They see like open lanes where planets have been forming and clearing out material. So we have evidence, even from early stages, that the planets are forming early on. Have there been any Tatooine planets been found? We haven't found any yet, but I'm sure there's some out there. It's very hard to study them.
I'm going to take the last question here.
Last question, okay.
Maybe you will get this.
Could you tell us a little bit more about TESS and that? How long does it do a strip? Is it like, because it has to be long enough to see it transit. And then my second question is Barnard star. Can you tell us about the exoplanet?
Sure. Okay, let's start with Barnard star. It's a really nearby M-dwarf star, and it happens to be moving very quickly with respect to our star system. Let me think. Yeah, I think there's evidence of a planet around it, and it's evidence of an Earth mass planet. It doesn't go in front of the star, but a different technique has revealed its presence, so it's pretty exciting. As for TESS, let me just try to wrap it up quickly, but okay, so TESS orbits Earth, and you know how our Earth is also orbiting our sun? And the sun is super bright. You don't want sunlight getting into the telescope because then you can't observe the stars. So just by its orbit, it can only look for 1 month at a given strip of the sky because of the sun will get in the way. And sometimes the moon is a problem. So TESS looks at every strip for 1 month. Now you'd like to see 2 transits, okay? You want to see it one time and then another time, so you know it's a planet and it has a period. And that limits you to planets that are about less than a month, actually. But as TESS has been living on for many years, it can repeat parts of the sky, and then you have a shot at finding a planet with a longer period. There's even a more complicated way if you see a single transit to do some clever ground-based follow-up and try to catch a second one. So it has found planets as long as like 100 days through clever methods.
The last.
How about one last question? Yes.
I was wondering, in the course of trying to identify means of communicating and sending a probe very, very long distances, have you ever considered partnering with people who are studying the absolute opposite, the very smallest size inside of us, to look for parallel ways that very, very tiny, things that are inside of ourselves that are traveling and sending communications like insulin signaling, et cetera, and looking for those parallels in the...
No, people have not thought of that only because everything spreads out and gets so much weaker with distance that we haven't thought of that. And I think I just want to say 2 things to close up. One is, okay, you should be reading the book because they think about that and it's very science fiction-y and it's super far in the future. But honestly, that's kind of what the book, The Three-Body Problem, captures some of that. I just want to thank you for being a great audience, and thanks for your attention.
Thank you. Before it's wrapping up this evening, we do have good news for high school students. How many high school students come tonight? Wow, quite great. Thank you. So as Professor Seager mentioned about, we do have nice telescope, that means we can study exoplanets. So if you have questions, we do have Professor Ben Gold, kind of this expert. You can stay and ask him about the question. We also have 2 summer camp is coming. It will be in July 2025. One is a young physicist camp. Another one is microscope adventure camp. So thank you all for coming. Let's thank our speaker again. Okay, enjoy the evening. Thank you all for coming.